can you see this presentation?
Sir, yes sir, yes sir. It's visible,
Okay.
sir.
Okay, thank you. So can I start the presentation?
Yes sir, sure.
Okay, thank you. Oh. Okay. So thank you. At the outset, I thank the organizers for inviting me to give a talk in AICT sponsored FDP program. My today's topic or talk is 4E analysis of solar rated coal-based thermal power plant or thermal power generation. So I think Exergy and thermoeconomic investigations in power generation are very important, and if we go with the 4E approach, energy, exergy, environment, and economic analysis is a comprehensive analysis for any power generating system. So therefore today's talk is on integration of coal-based power plants with solar system, so that there is a possibility of fuel saving as well as the improvement in energy efficiency. So with that, I will give you the basic information of this. I think why the 4E analysis is important for power generation, and what is the role of solar integration in power generation, I am going to discuss today. And before that, I'll give you general introduction, mainly for sustainability purpose. So we are facing several problems: energy, water, food, environment, poverty, terrorism, war, diseases, education, democracy, and population. So therefore, it's important that energy problem cannot be addressed in isolation. So therefore, energy environment is an important. So that is why we are calling it a 4E analysis: energy as well as in terms of quality and quantity of energy, as well as environment and economic analysis. So food, water, clean energy are very important. If there is these three things are important. Out of all these problems, energy can solve most of these problems, and the world's primary energy is increasing very rapidly, and it has been exponential growth. So therefore, the energy consumption is rapidly increasing because of the industrialization, development in standard of livings, and then of course population growth. So therefore, the standard of living of any country depends on, or an individual depends on, energy consumption. So therefore, it's very important to do comprehensive analysis of this energy system analysis. So in terms of exergy and thermoeconomic analysis of the power generation, most of the power generation across the world and India is primarily based on fossil fuels. So therefore, it has its own adverse effect on environment. So therefore, in order to minimize and mitigate the environmental issues, so it's very important to go for energy and exergy analysis of the power generation. So these energy sources are broadly classified into two categories. One is the celestial or income energy, and capital energy. Energy reaching the Earth's from outer surface is called income energy or celestial, and this energy sources include solar, lunar energies, which we refer them as a non-depletable, electromagnetic, gravitational, particle energy from stars, planets, and the moon, and potential energy of meteorites entering into the Earth's atmosphere are referred as celestial or income energy. Capital energy is the energy that is already existing and or on the Earth. Examples of this is mainly fossil fuels, like chemical form of energy, and nuclear energy, and geothermal energy, which is in the Earth crust. So generally, the capital energy is the source which is already present in the Earth's crust. So therefore now for power generation, see, you know that power means electricity. Electricity is the one of the most most effective, or you can say more high quality form of energy, highest quality form of energy among the all energy forms. So therefore utilizing electrical energy for our requirements depends on how we produce that. So therefore producing a cleaner energy is a better option. Then if you look at the energy reserves, they are broadly classified into renewable or non-depletable sources, which include solar, wind, biomass and ocean. Second one is fossil fuels, coal, oil, gas, and then nuclear, both includes fission and fusion reactions. If you look at the energy system hierarchy, it is we have primarily energy sources and then energy carriers and then equipment and services, and this is the hierarchy of energy system. And we have essentially the fossil fuels, coal, oil, gas, and then biomass, nuclear and renewables. Then they are converted into a secondary form of fuels, and that is either it could be high quality energy like electricity or liquid fuels, whichever is these are essentially energy carriers, and those are used at as per the consumer choice, whether it's mobility or whether it's some building operation or any other operation. This is a typical energy system hierarchy depending upon the energy transformation effects. So therefore it's very important to know the impact of this. And if you look at the global energy potential here, we have coal, fossil fuel, coal, oil, gas and uranium. These are the respective potentials of these, and then followed by natural gas, wind, biomass, and you can see these each size of the circle is represent the amount of energy that is present. You can see if you go further, there's a small tidal wave, geothermal, hydro sources. But if you, this is the energy, world's energy demand or consumption, and this is the current consumption. If you try to meet this energy demand by coal, oil and natural gas, they extinct. So therefore, if you look at this bigger one, which is the sun, that is a huge potential of this. Even if you consume with this, it's more than required, and it can last several hundreds of years. So therefore, it is again inexhaustible source. Therefore, it's important to tap on solar energy for power generation. So that's what I emphasize. If you look at the energy demand and prosperity across the world, wherever it's highly illuminated, there you have energy demand and prosperity. Wherever it's less illuminated, there's a less energy demand and prosperity. That means these are night lights which illuminates. So you can see wherever we have a higher, this one and here. So this part is a little bit non-uniformly or uniformly distributed. So therefore, we can see that there are many areas in this are dark. So therefore, you can see that the global energy poverty, and especially the in this region, SAARC region, there and the South African region, about 1.6 billion people have no access to electricity, and 80% of them lie in this area. So if you look at this, India, Pakistan, Nepal, Bangladesh, and Sri Lanka, still several million people are deprived of the primary energy, and they're dependent on biomass, and a million people do not have access to electricity. So therefore, it's very important to produce electricity, this high quality energy, with the renewable energy source. Energy sustainability is very important. The energy sustainability can be achieved through make use of renewable energy. We feel we deserve this type of thing, because I can say that all energy sources are being imported in India, because we import coal, we import gas, we import oil and import nuclear energy. So therefore, if you import these fuels, mainly fossil fuels, and then try to burn in Indian conditions, then obviously it will have a adverse effect on environment. So Indian fuel, Indian foreign coal, foreign fuel, and foreign technology, and if you burn it in India, obviously it will have an impact on Indian environment. So we feel we deserve for this, but eventually we'll end up into that. As you know, that the fuel prices are going up and highly volatile, and then their substantial improvement in utility, and the rate at which it's growing is substantial, and eventually the burning of these fuels will result in environmental issues. Apart from the environmental issues, there is a shortage of power, if a shortage of fuels. So this shortage may result in ultimately landing up nowhere. So therefore, energy sustainability is very important, and you look at that this is a bluish color earth, and it is surrounded by the air about 15 kilometers or so, and because if you do anthropogenic activities like the energy consumption by human beings on the earth will result in emissions to the atmosphere, and the atmospheric air is getting polluted, and of course water bodies are getting polluted. Because of this excessive emissions into the atmosphere, this bluish color is completely imbalanced. We are literally burning it off. So therefore it is an important thing to take care of the earth, and coming up with the appropriate technologies, appropriate energy technologies. So therefore, if any overloaded system, if you overload the Earth's atmosphere, any overloaded system looks like this. If you put too much load, what happens is it gets imbalanced. So therefore, energy sustainability is very important. The energy sustainability in terms of resources, if this is what if we have resources, and if you start to drain, if they are fossil fuels, and if you try to consume them, this will become empty at one point of time. That means the resources may exhaust. So therefore, this may not be a sustainable option. Therefore, it's very important to come up with a indigenous technology and to keep these resources for the future generation by having a technology so that these resources can be kept for the future generation. We can take care of our own share of fuel or resources here. So, but for that we may need the technology. This technology is an energy technology which keeps the resources sustainable. So therefore, that energy technologies are renewable energy technology. So therefore, we have to, our future generation says that there is only one earth we have to take care of, otherwise the earth will become unconducive for living. So therefore, the energy sustainability is important, and this energy sustainability could be achieved through energy efficiency, proper mix of energy sources, make use of renewable energy technologies or renewable energy sources. So therefore, there is a barriers to bridge the gap, bridging the welfare gap, mainly in order to obtain the reliable energy supply. The energy supply is very important. There are several barriers for bridging this, and those includes transportation bottlenecks and increase in energy demand, domestic unrest, and energy investment, market deregulation, energy price volatility, and developmental technological development, geopolitical instability, increase in energy imports, and so on. So what I mean to say here is there are several bottlenecks for supply of energy. That includes, of course, now you can see that there is a demand increase, substantial increase in demand, as just now mentioned, that because of the industrialization and increase in population and increase in standard of living may result in increase in energy demand. But then whether this energy demand can be fulfilled by the Indian or indigenous fuels, obviously at this point of time no, because of we import coal, oil, gas, and almost the oil is say more than 70% or about 70% is being imported. So therefore there is a domestic unrest, and the investments that are going in is also very important. market is deregulated, and then the prices are highly volatile. Every day the petrol prices are getting changed, and then there is energy. There should be technological development for energy efficiency, but apart from that, there is a geopolitical instability which may result in mainly the OPEC countries. They cut the production, then obviously the prices will go up, and increasing energy imports is another major problem. That is why the government, mainly government, is interested more to dependent on indigenous fuels and so on. So therefore, energy security is most important for the country like India. So therefore, energy security is the continuous and uninterrupted availability of energy to a specific country or region. The security of energy supply conducts a crucial role in decisions that are related to the formulation of energy policy and strategy. So threats to energy security can even due to natural, technological, or human causes which lead to disruption or damage to the damage of energy system. So therefore, energy security is very, very important. Otherwise, if energy is not secured, it may result in highly unrest among the people. So therefore, there are technical challenges stabilizing the greenhouse, because we are talking about power generation, exergy and thermoeconomic analysis of power generation. So the power generation, there are several challenges, mainly to stabilize the greenhouse gases concentration in the atmosphere, but there is no single technology or policy can do it all. So therefore, it depends on the region, markets, scale-up requirements, infrastructure, technology timings, preferences, and resources. So then one can think of vehicles like energy efficient vehicles, biofuel vehicles, hydrogen fuel vehicles. We are talking about EV, electric vehicles, and so on, and going for new technologies in building sector, because building sector is one of the high intensity, energy intensity sector, because most of these buildings are enclosed with glass and other things, and they require space conditioning. So therefore, net zero emission buildings are important. Industrial efficiency is another option, even industrial buildings. CHP, combined heat and power, is another option for such buildings, and so on. So nuclear power generation with the 4th generation technology is an important thing, and apart from that, the fossil fuel combustion results in emissions, and mainly the carbon dioxide is a major environmental gas, environmental degradable gas. So therefore, it needs to be captured, and that is a carbon sequestration. It should be captured properly and then stored in properly, so that the CO2 is absorbed and used for other applications. Advanced grid transmission distribution of electricity is also very important, and as you know that there is a lot of power losses during transmission and distribution, and it may result in very large amount of losses because of this T&D losses, and that is why we need to transport the electricity in a most efficient way with less losses. That's what we call advanced power grids. There is a necessity for that. And then biofuels and power generation is another important aspect, and then renewable energy technologies plays a major role in technological challenge. Everywhere in this EV vehicles are net zero buildings, are nuclear, carbon sequestration, advanced power grids, everywhere the technology plays a major role. So therefore, a single technology cannot address the problem of this. There are several challenges, and these technologies eventually results in stabilizing the greenhouse gases concentration in the atmosphere, as we are experiencing the global climate change, and that may be very, very dangerous level, and so therefore it's very important to stabilize the greenhouse gases. Now, if you look at, because in Indian context, the power sector, power is, I mentioned, is the highest quality of energy among other forms of energies like thermal, electrical, thermal, and other forms, mechanical, and other forms of energy. So therefore, it is in thermodynamics, you have two quantities like heat and work. So heat can be converted into work, but not completely, whereas the work is completely converted into heat. So therefore, work is more valuable than that of the heat. That means more quality than the heat. So therefore, it is important to come up with a work in terms of power and so on. So if you look at the power generation in India, it is increasing slowly, and per capita electricity consumption is increasing rapidly. Now it is somewhere close to about 400 to 500 kilowatt hours per person per year, but it needs to be increased up to 3000 per per kilowatt hours per person per year. I think it's projected that the energy consumption is rapidly increasing. So therefore, if you look at the current projected installed capacity based on the different sources, you see the coal is highest now, but this is also gaining, renewable energy is also gaining importance. So therefore, hopefully there is a lot of potential. But now in another at least 2 to 3 decades, the fossil fuels continue to be, like coal is continue to be a major fuel for power generation. So therefore, if you look at this reserve to production ratio of various fuels like oil, only 30 years, and natural gas is only 30. See, the present reserve to production ratio is that the present resources which are available, if you use with the same rate, how long they can last. So oil can last only 30 years, natural gas can be about 28 years, or coal is about 100 years they can last. And coal is the only one which has we have good sources, reserves, but the even it is on par with the world's average. So therefore, the coal can be utilized, but the coal has its own adverse effects. Then India is the 4th largest producer and consumer of the coal. So therefore, we have reasonably good reserves as far as the coal is concerned, but the coal has its own. We have high ash coal, and but of course the low sulfur content, which makes environmental better, but the calorific value point of view, it's very low. So can you hear me? Is it connected?
Yes, sir. Yes, sir.
Okay. Thank you. If connection is lost, sometimes we may lose connection. Please let me know.
Definitely.
So yeah, the current sources wise power scenario, if you look at that, it's varying differently. Again, as I mentioned, that coal is a dominant fuel, followed by the other renewables, and electricity also because if you look at this capacity factor of the coal is much higher than the renewables, like solar. Solar can produce only 8 hours per day, whereas coal you can produce power from coal 24 hours. So therefore, load factor, capacity factor is also much higher as compared to that. But we need to improve the reliability of renewables by using battery energy storage system, or thermal energy, or battery energy storage system, for making them more reliable. So it is very important to look at this, why we are going for 4E analysis. If you look at the per capita energy consumption is in India is somewhere this, and then world's is this, and of course the other developed countries are much higher. So therefore it's necessary that we should improve the per capita energy consumption without affecting the environment. That is why it is an holistic or a comprehensive analysis of this power generation is required through 4 E's: energy, exergy, environment, and economic analysis. It is a comprehensive analysis to investigate the efficiency, energy utilization, environmental degradation, as well as the economic viability. So therefore, that's why we call it 4 E's. Challenges: the plant efficiencies of Indian power plants are relatively lower, high ash coal and high cooling water temperature, because as you know that most of you are mechanical engineering students, the power generation is operated actually produced by a heat engine which operates between two reservoirs, and takes from a higher heat source and then convert into W work and then produces rejects the heat into the atmosphere at some atmospheric temperature T2. So therefore, in India, what happens is most of the time this T2 is much higher, and as you know that the efficiency is given by 1 minus T2 by T1. So therefore, T1, this T2 is much larger as compared to other countries. That is why the temperature is even, sometimes it goes 50 degrees, but if you take average water cooling water temperature itself is 33 degrees Celsius, unlike European countries where the ambient temperature is much lower. So therefore, this is another reason for low efficiency of the power plants, and ash content is another source. In India, we produce, consume and produce coal substantially, fourth largest producer and consumer, eventually fourth largest emitter of CO2, which is an environmental problem. Though the quantity wise is higher, but the per capita CO2 emissions is concerned, it's much lower because our per capita energy consumption is very low. So therefore, it is very important, and it's a challenging thing to come up with a comprehensive analysis of power generation so that it will have a trade-off between energy, environment, and economics. So we are doing a 4E analysis of power generation. I have primarily focused on general power generation, coal-based power generation. How do we include solar energy so that we can reduce the coal consumption as well as the environmental degradation? So we can reduce the environmental degradation. Not only that, but also we can save some fuel. So therefore, in order to do that, comparative system analysis of our advanced coal-based power generation technologies with respect to energy, exergy, environment, and economic analysis, where we call them as 4Es, and their comparative performance assessment to propose a strategy in the context of prioritizing power generation technologies for high ash coal like Indian coals under Indian climatic conditions because of higher atmospheric temperature. So if you look at the reserves, which I have already mentioned, but if you look at, this is the energy consumption, but these are the sources which are available, but they are, if these sources are used in this fashion, they may extinct respectively these number of years. So coal can last only 119 years, oil can last 46. This is a global phenomenon, though we have given the Indian. So if you look at the coal this one, oil can only last for not even one generation, and these are the Indian statistics against the world statistics as far as the coal, oil, nuclear is concerned. They may extinct in couple of years, and we may not be able to find this. So therefore, it's high time to come up with a exergo thermoeconomic analysis of power generation in order to identify the inefficiencies, irreversibilities, and also improve the performance. Then we'll go for what is the scope of 4E analysis. Since because the audience are very broad, so I will cover various power generation technologies with respect to 4Es, both conventional advanced power generation technologies, mainly typically for high ash Indian coal, and imported. We can also compare. We import coal, most of eastern coast and western coast import coal from Indonesia, Australia, and South Africa. So therefore, these imported coals have low sulfur, low ash, but high sulfur, the 2% sulfur. Indian coals contains only 0.5% sulfur, but 30 to 40% ash. Whereas imported coals have about 10 to 12% ash, but 2% sulfur dioxide is harmful. And another important thing is Indian atmospheric temperature 33 degrees is taken as average, and based on this we have done analysis for supercritical power plants and subcritical power plants, supercritical power plants, and ultra supercritical power plants. Based on this, we come up with different combustion technologies also. The combustion based technologies include pulverized coals and the ACFBCs, PCF. I'll tell you what are these. PF is a pulverized coal fired combustion. ACFBC is the atmospheric circulating fluid as bed combustion, and PCFBC is a pulverized circulating fluid as bed combustion. OCCC is a oxy coal combustion. PCC is a pulverized pressurized pulverized coal combustion, and IGCC is the integrated gasification combined cycle. Subcritical is and supercritical and ultra supercritical power plants, and finally this one, the solar thermal aided coal based power plant. My talk is basically hybrid technologies, this, and optimizing the most relevant power generation technologies, and optimizing PF subcritical, PF ultra supercritical, PCFBC subcritical with supplementary firing, and IGCC and IGCC subcritical power plant configurations have been studied, and comparative Fourier analysis and evaluation of various advanced coal-based power generation technologies based on constant gross power output of 500 megawatts and above. We are talking about 660 megawatts and so on. So therefore, the scope of this Fourier analysis include this, but finally I will only discuss the solar rated coal-based power generation. So before that, I think already, I think this is today is the second day, I think. So therefore, you have already heard about exergy, energy, what is the difference between exergy, energy, and so on. So, but nevertheless, I'll give you some information related to that, because this is my point of view. So you look at this exergy. Actually, generally exergy is equal to energy minus energy, which are losses. So here you have energy is and losses. So therefore, there is a this tells quantity and this tells quality of that. Exergy is the maximum work obtainable as the system comes to equilibrium with the surroundings. The higher value of exergy, more is the work obtainable from the system. So you know that we discuss about first law and second law, but first law tells us quantity of energy and second law tells about quality of energy. The first law of thermodynamics makes only an energy balance of the system or control volume. It doesn't make any distinction of different forms of energy, particularly between work and heat, or heat available at different temperatures. It means internal energy. So it is the second law which asserts that from engineering point of view, all forms of energies are not of the same quality. Energies of two systems may be quantitatively equal, but qualitatively they may be different. So, for example, if you take steam adiabatically throttled, and the energy does not change, but the quality degrades. Exergy is the measure of energy quantity, energy quality, and exergetic efficiency is a measure of perfectness of the thermal systems, while energy of the system is in any process remains constant and part of its exergy is always destroyed. This is about exergy. Then I'll give you some configurations. If you see the connections among various other forms of terminology like exergy, availability, exergy, free energy. So I have given mathematically here function. This is the exergy function. This is a value of this, and then energy plus PV and then minus TDS. This represents heat quantity. Availability is this. Exergy is defined as this. So now exergy is defined as this way. E is the internal energy, P is the pressure, and V is the volume, and T is the temperature, and S is the entropy, and so on. So free energy is another, like Helmholtz or Gibbs free energy is given by these, and their description are given here, and you can see that there are several indicators of this, and then it's given in this fashion. But I am not going to discuss. Then when we look at second law analysis, we generally come in effectiveness or exergetic efficiency. Effectiveness is given as the theoretical maximum available work to accomplish, divided by the available work to accomplish the task. So it's a ratio which is also represented by epsilon. That means if it's a ratio of energy, work, heat, or work usefully transferred by a system to the maximum possible heat or work usefully transferable for the same function using the same energy input as the given system. So the factors, because generally there are inefficiencies involved, there are several factors which influence the inefficiencies. The factors which contributes inefficiencies are losses, and which results in loss of energy or availability, and these includes several of those, and they differ from energy to energy. For example, if you look at the mechanical energy, it's a friction, impacts, and damping are the major source of irreversibility. Fluid energy is the line losses, fluid leakages, flow restrictions, fouling, corrosion are the major source of energy loss. Heat energy, it's by convection, conduction, radiation, infiltration, extrafiltration are the major sources of irreversibility, because the heat transfer cannot the heat cannot be transferred at constant temperature. So therefore, it has to, in order to transfer, like either through convection, conduction, radiation, it is a basic requirement is there should be a temperature difference or temperature potential, delta T. This delta T results in the transfer of heat. So if delta T is higher the potential, but of course higher the losses also. So therefore, the conduction, convection, radiations cannot be at constant temperature. It cannot be isothermal process. Heat transfer cannot be isothermal. If it is isothermal, it is because when their two temperatures are same, you cannot transfer the heat. So therefore, it needs a temperature gradient. If temperature gradient means delta T, that delta T may result in irreversibility. So therefore, it is also important to have irreversibility to take care of. Apart from that, the electrical energy, mainly I square R losses, eddy current, hysteresis and recharge, line losses, several of these are involved in this. And of course, loss of availability through combustion, pressure drop, temperature drops are the major sources for factors that are contributing to the inefficiencies of the system. How do you write the second law efficiency? The first law and second laws of thermodynamics for steady flow process with the multiple inlets and exits can be expressed into this Q dot minus W is equal to this sigma mu. This is the exit minus entry streams. So the second law based on the entropy generation always greater than equal to 0. So therefore, entropy entropy at the exit minus entropy at the entrance, and of course by the surroundings. So here where Q surroundings is minus Q, because it's given to the atmosphere, it's lost to the atmosphere. S generation is the entropy generation of the process. Eliminating all heat transfer terms, we come up with a comprehensive analysis of work transfer, and this is the actual work done during this process, and which is also useful work since the steady flow devices have fixed boundaries and do not involve any work done by or against the surroundings. So therefore, this is the second law equation based on this. And if you look at the reversible work obtained by setting up the entropy generation term equal to 0, and then you can get the this equation. Subsequently, we can write with a single, because this for multiple, because we have written sigma here, so that therefore multiple streams. If you eliminate sigma, that means it will become a single fluid stream. This is a single fluid stream. In such case, the generalized equation is that. But then exergy can be given by this equation, which is irreversible work. So here you can say accumulation of non-flow energy, exergy transfer via heat transfer, intake of flow exergy via mass flow, release of flow energy via mass transfer, or the sum of the irreversibilities inefficiency. So if you replace that, you'll get the availability term, and this availability reversible work is change in availability, which can be given by this change of availability AI minus A naught. So the rate of irreversibility associated with the steady flow processes is also important. So you can see here irreversibility is given by reversible work minus the useful work, and so therefore it can be given as T naught into S prime S generation dot. So therefore this irreversibility need to be calculated for every process, and then try to minimize based on the this one. So based on the availability. So see what is the significance of exergy. You can look at this equation, generalized equation with multiple endless entries and exits, and the maximum work, and this is the last term where the energy work loss or loss of available work, it's always positive. So therefore the work is given by reversible work minus the work irreversible. So this is a irreversible work is equal to reversible work minus irreversibility. So therefore where the exergy loss is given by this term. So energy is always conserved, as I mentioned earlier, but what is not conserved is the exergy, and is used, that is useful work potential of the energy. Once the exergy is wasted, it can never be recovered. So improved energy source utilization can be realized by reducing exergy destruction within a system, or reducing the losses. An objective in exergy analysis is to identify sites where the exergy destruction and losses occur, and order them in significance. What I mean to say here, see, exergy analysis of power generation means you have to identify the sites where there is an irreversibility or exergy destruction or losses are occurring, and you put them in a sequence which is having, see, you have seen power plants. Power plant has 4 processes like heat addition, that is in boiler, and expansion in turbine, and heat rejection in condenser, and pumping. If you look at these 4 components, where is the highest irreversibility, you prioritize and put them in order of significance where the high irreversibility exists. So therefore I will give you a simple Rankine cycle. Just now I mentioned it involves 4 processes. You have heat supply at the source, and turbine is expansion, and then heat rejection in a condenser, and pump work is added to bring back to the system, and it undergoes cyclic process. So the exergy analysis of each steady flow component of the power cycle allows us to determine the distribution of the irreversibility among the cycle components. So therefore, where we find high irreversibility in these 4 components is important. Then accordingly we can fix the problem and improve the performance of the power generation cycle. The Rankine cycle consisting of 4 steady flow components: pump, heater means boiler, turbine, condenser operates between TH and T naught, and the energy interactions experienced by the components are indicated in by arrow that point in the correct physical direction. This you can see the directions of that arrow here. This arrow is going out, and this arrow, and this arrow, and then the work is in here, here, and then work is out, and then heat is in and heat is out. So I'll give you one simple combustion process, exergy analysis of combustion. This is given by this equation. It's a chemically reactive system. The standard Gibbs function change is given by that, and change in enthalpy formulation is delta H, and this is in terms of minus NCV. Then based on that we can come up with these functions and these functions because I'm not going in detail, and then this is the Gibbs function, and finally we get heat in terms of this T into delta S, that is the Gibbs function energy. Now if, for example, if you this phi, the phi is an important value here, the phi value of phi for given for different fuels like coke, coal, wood, fuel oil, petrol, like this, their values are mentioned here. So therefore, in second law analysis of mainly vapor cycle, we need to find out irreversibility. Irreversibility of steady flow systems, most the steady flow energy equation, exchange heat with the reservoir at temperature Tr, and can be expressed in terms of I naught, I dot, and that is T naught into S generation dot, and that given by the previous equations like that. When you have a multiple entry, sigma will come, and multiple exits. Irreversibility of any steady flow system, consider the unit mass and single inlet and single outlet, then you can eliminate the sigmas here. Then you will get this, which is dependent on per unit mass is I, not capital I. Vapor cycles, the amount of irreversibility can be determined by finding the change in availability of process, that is availability of process with reference to enthalpy, with reference to heat, and then with kinetic energy, potential energy, and so on. So therefore the datum or reference point is taken as H0, where the energy transformation occurs or availability occurs. So our methodology, though I mentioned 4A here, that economic analysis will come later. So therefore, for the energy, exergy, environmental analysis carried out using flow sheet program, so which we call Cycle Tempo. It's a Cycle Tempo is a software which is flow sheeting program, and mainly essentially here mass balance is done, and energy balance is done, and exergy balance is done, physical energy balance and chemical energy balance, and finally chemical species balance have been done with these, and these are the parameters. Anyhow, you go through that. The performance parameters which we need to study is plant energy efficiency, plant exergy efficiency, specific CO2 emissions, and annualized and levelized cost of electricity generation as a part of our 4E analysis. So if you look at the coal characteristics, as I mentioned that Indian coals contains high ash, whereas imported coals have low ash coals. That is why you can see here coal characteristics, Indian high ash coal, based on these you can see as received, and then by dry basis, when the coals comes on its own, it's called as received. These are imported coals, you can see here. These you can see fixed carbon is higher and volatile matter is comparable. This mineral matter is much, that's ash which reduce less, and then this moisture is also less as compared to Indian moisture, about 12%. So then if you look at ultimate analysis, then different constituents of the fuel can be found, and based on the calorific value, you can see the calorific value of Indian coal is 13.96 megajoules, whereas foreign coal is 26.83 megajoules. And exergy, if you look at, it's almost double exergy as compared to this. So therefore, based on the exergy can be coal can be calculated by this complex equation, and the efficiency is given, plant exergetic efficiency given by net electrical output by mass flow rate of coal into specific exergy of the coal. Whereas here HHV high heating value of coal, but here specific exergy of the coal. Now we have taken a typical power plant configuration here. You can see it's a configuration of 660 megawatts supercritical power plant. This is a pulverized fuel. FP means pulverized fuel supercritical power plant. And the fuel configuration, you can see here, the air comes from this and goes to the combustor here. Coal is burnt from here, and then flue gases goes like this and goes out. Okay, this is a boiler. You can see here, this is boiler one, and we have high pressure turbines, intermediate. Here this is a high pressure turbine, and then the intermediate pressure turbine and low pressure turbines. And this steam is distributed among the this. See, first from the superheater. From superheater, it goes to the turbine, high pressure turbine, and from this it goes to the some part. It goes to the feed water heater. Rest will go to the reheater and then come back like this to this, and then from here, from expansion, it goes here and here. So therefore, we have different types of. This is a opted from NTPC configuration. So therefore, you can see various pressures, temperatures, and reheat temperature and reheat pressures. So these are given here for various subcritical, supercritical, advanced supercritical, and ultra supercritical power plants with a different. You see that live steam pressure can go up to 30 megapascal, and live temperature can go more than 100 degrees Celsius, and reheat steam is also greater than 100. This configuration we have done. One of my PhD students has carried out this, and for different coals with the different capacities, we have considered here 4 different capacities of configuration: 500 to 500, 660 supercritical, and ultra supercritical is about 430. And based on this, the plant efficiencies, you can see that supercritical how drop. The ultra supercritical is much higher efficiencies. So there are about more than 5% percentage points. So comparison of specific fuel consumption, it's substantially reduced. You see that ultra supercritical power plants are less as compared to this one. So what is the meaning of this is increase of 1 percentage point in plant efficiency, energy efficiency of a 500 megawatt subcritical power plant from 35 to 36, for example, will result in approximately about 4.5 crores savings annually in the fuel cost. But this is a bit old data, but now if you can see, it's almost another 30-40% higher, and the capacity factor is about 85%, and HHV is assumed to be this, and the coal cost is 2,000 rupees a ton, but now it's a bit expensive. And then based on the pulverized coal combustion technologies, the comparison of energy balance at different conditions, cooling water, power plant, and rejected through stack and rejected through bottom ash, other losses is that, and the heat rejected in a cooling tower is substantially higher as compared to the C. If you look at the what is the purpose of exergy analysis, we can identify where irreversibilities exist. So then you look at this heat rejected in cooling water is almost 2/3 of the power. Only power efficiency is 35%, but almost double the heat is lost in environment. So this is the major thing. So that means there is a huge source for irreversibility in this particular component. If you compare with all of these with the exergetic balance, the loss in combustor, loss in steam generator and all is given. You see that the major losses are in these exergetic thing. So if you look at energy point of view, this is the table, and exergy point of view, this is the table. You can see the difference, how the loss, mainly loss in combustor, loss in steam generator are much higher as compared to the other. They are minor. Last in condenser cooling water is about 2.1% and so on, and then you can see it differs from various options, both low heating value and a high heating value fuels. Now, if you see the results, pulverized coal combustion, if you look at that, we can operate design condition or part load condition, because most of these power plants do not operate 100% all the time. So therefore, if we have considered minimum of 40% partial part load condition, and maximum is full load is 100%. And then you can look at the different, see the ultra supercritical power plant is this, and then you can, this is a plant efficiency versus loading. So here this is different configuration of the power generation, this power generation configuration. This is more of plant efficiency with different controls and control mechanisms, how we can get it. So sliding pressure is an advantageous than the throttling control for part load operations. Then effect of condenser pressure on plant efficiency. Indian condenser pressures are different because they are dependent on the local wet bulb temperature or saturation conditions of that, and the plant efficiency and plant exergic efficiency are dependent on the condenser pressure. So as the condenser pressure increases, the variation in plant efficiency decreases. Then that is the major thing which you can notice here. Condenser pressure, as the condenser pressure increases, the plant efficiency drops here. Apart from the high ash coal, and the major limitations is higher condenser pressure in Indian climatic conditions, because our climatic temperatures are average 33 degrees Celsius. You see, this is 33 Indian ambient condition is considered. Based on that, high ambient conditions result in higher condenser pressure, because this is you have to come up with the saturation pressure corresponding to this temperature. So therefore, similarly, if in India can be operated much lower pressure here. Almost see, it's 0.1 and here 0.03, almost 1/3. And the for example, in Germany, the ambient temperature is 25, we have considered 33. So therefore, higher ambient temperature means less efficient. So optimization of steam cycle parameters has also been done with the different conditions. We compared both India and Germany conditions here from future this thing, as the pressure and temperature. We are talking about 350 degrees and 700 degrees Celsius. See, in operating very high pressures and temperatures, the materials have to be very strong. Otherwise, the material cost will go up drastically. Metallurgical parameter, every 50 degrees increase in temperature may result in almost 30% weak. The tubes will become weaker, because so therefore we have to go for thick tubes, boiler tubes. So therefore, current supercritical parameters in India are way beyond the state-of-the-art technologies. So therefore, the flow chart of this includes determining the condenser pressure, and also select low pressure turbine inlet, and subsequently select of main steam pressures and temperatures, and select the reheat steam and reheat pressures, steam pressures and temperatures, and select the final feed water heater temperature. And based on the pulverized fuel plant optimization, the effect of main steam pressure has also been seen, and the temperatures are up to 700 degrees Celsius. And this is a steam pressure versus the change in plant efficiency. As we increase the steam pressure, there is an increase in plant efficiency in terms of percentage points. And so main steam pressure about 290 bar for supercritical pressure, and 350 bar ultra supercritical, and main steam temperature for 600 for supercritical. Temperature is this and pressure is that. And here this is the pressure, and this is the temperature here. So maximum temperature can go up to 700 degrees Celsius, and whereas pressure is 350 degrees Celsius. Effect because in generally supercritical power plants have generally two reheats. Let's see, if you go for reheats, first reheat effect is also very important and is substantial. We have to see that the ratio of reheat to the main pressure, where that pressure is then, and reheat steam temperature is almost 20 degrees greater than that of the steam temperature. So reheat temperature should be higher than the main steam pressure. So the pressure is low, but the temperature, as you know, this reheat is like this. If you have a power plant cycle, it goes like this, and it goes, and then it comes here, and then goes like this. So this reheat pressure is low, but the temperature of this is higher than this. Is about 20 degrees higher. This 20 degrees is higher as compared to the reheat, but the pressures are low. So therefore, about 620 degrees, this TS diagram. Then if you look at plant optimization with a second reheat pressure, if you in that case I have shown only single reheat, but you can further go and take it. This pressure is also mainly this is possible when you go for supercritical pressures like this, supercritical power plant cycle. So the effect of second reheat steam pressure is very important, and it can be done here. First reheat at 85 bar and second is 26 bar. So you can see, and the temperatures are plus about 20 degrees. And we can go for either single or double reheats with the different ultra supercritical, and temperatures are given here. Corresponding things are here. If energy efficiency and exergetic efficiencies are given here. If you drop about 60 degrees in low pressure turbine inlet temperature by migrating to reheat ratio of 0.3 instead of 0.2 and dryness fraction 0.97, and the reheat ratio of 0.3 to dryness fraction 99, the reheat pressure is this. So then if you look at optimization, these are the optimum parameters with these are the finally evolved this, and it is also major biggest plant is to consider in this case is the 800 megawatts supercritical power plants with this is the configuration, and the corresponding feed water and steam qualities are shown here. And the performance parameters of subsequent optimization of 800 megawatt PCC, supercritical and ultra supercritical power plant configurations are shown here. You can see that. Then this is a single reheat supercritical is shown in this fashion. So here supercritical, this one is important here. The optimization of various operating parameters of the power plant simultaneously is changed, and the mainstream reheat stream pressures and temperatures of turbine extraction pressures and excess air ratios are all very important in this case. Then we went for another technology of neural networks and genetic algorithm based pulverized fuel plant optimization. This is the methodology which is almost similar to that, and then we have used cycle tempo as well as neural network power plant is simulated, and then these are some of those parameters here, and then the output energy is found for the given input parameters by applying G. And this is a basic architecture of the neural network with a different input parameters, and ultimately you have to get the maximum heat output here. And then this is some parity chart for the analysis of the verifying the ANN network and this one. Then Exergy output is calibrated and validated with the generations and found that it's important. So now ANN based optimization is done here, and then excessive air of 20 to 18% depending upon. See, this is the parametric optimization parameters, and this is based on ANN tool. So therefore they are comparable to 20% against 18% and so on. These are different conditions. Then we went for oxy coal combustion. You know that we burn coal. As I mentioned that Indian coal contains high ash as well as this one. So the combustion requires a large amount of air. When you go for air combustion, obviously what happens is the nitrogen, because air contains almost 71 or 79% of the nitrogen, and rest only oxygen. So therefore this nitrogen is almost, you can see here, 70%, 71%. That is what happens is this nitrogen reacts with at higher temperature and becomes NOx. NOx is another major source of environmental problem. So therefore, in order to reduce this NOx, we better, instead of burning air, you burn with oxygen. So oxygen is direct burning of oxygen. So therefore, that may call oxy-coal combustion. Instead of using air, it will be burnt. See, this air is first air is taken from the atmosphere, and then nitrogen is let out into the atmosphere, and then oxygen goes into this, and then fuel is burnt here, and then this is a typical this. And once this comes out, then there is a recirculation here, recirculation, and then the electricity is produced by this. This, if you translate that into the cycle, it looks like this here. This is a recycled fuel gas control flame temperatures, and also make most of these things. Oxy-fuel coal combustion characteristics here, various losses, percentage of power efficiency, then where this is the efficiency 28%, and remaining are the losses. Most of the heat rejected to the condenser here. These are 41%. And it is been compared with the reference plant to the other reheat, double reheat, and ultra supercritical and some supercritical power plants. This is oxy combustion plants values here, and you have efficiency of these, and but the losses in flue gases are more here, and so on. So then if you go with PPCC power generation, so here it is a 62.5 megawatt pulverized, pressurized pulverized coal combustion. PP means pressurized pulverized coal combustion. So 62.5 megawatt pulverized fuel plant repowered with the PCC, because we consider about first this one, and in pulverized, if we add pressurized pulverized combustion, how it will impact. So design plant is 62.5 megawatts, and the repowered means we increase the power to 160, and subsequently the plant efficiencies are substantially improved, both exergetic and energetic efficiency. And then there is a reduction in CO2 emissions here. Then some of these results, efficiencies are given here, 31%, losses in combustion are given here, and ultimately the other losses are here. So therefore, low ash coal results in about 1.8 to 3.5 percentage points, improving energy and exergy efficiencies. Then if you go to IGCC, IGCC is integrated combined cycle. So gasification cycle, integrated gasification combined cycle. So therefore you can see that coal is not directly burnt, and coal is gasified. This system looks like this. The coal is burned, made into gas, and gas is used to run the gas turbine plant here. So the gas, hot gas cleaned up and then sent to the combustor, and then some additional heat is added here, and then finally it goes to combined power cycle, that is a HRSG, that is a heat recovery steam generator, and then it goes to the steam power plant, and then rest goes to the stack. This is another both high ash and low ash coal. It has been calculated. Always low ash will have a better efficiencies, like up to 45% and so on. This is a IGCC is an important concept, but of course that is a scale of operation is very important. And the various components like single pressure, double, dual pressure, triple pressure, and triple pressure with the reheat have been carried out, and these are some of the results. Only I am giving you here. See, IGCC, the conclusion is this IGCC does not appear to be the prospective option for high ash Indian coals. So therefore, because we have studied wide variety of power plants, but then for IGCC, Indian coal may not be very attractive because of the gasification and further losses in various components, including HRSG. This circulating fluidized bed combustion is this configuration here. There is a when we have shortage of domestic coals, increase in imports of low ash coals, blending of regular. So in the case we can go for circulating fluidized bed and then come up with a power generation concept. But ultimately the results are compared and analyzed with a different. I have given large list of coal-based power plants here, and their efficiencies are plant efficiencies, plant exergies are calculated, and what is the CO2 emissions calculated, and then levelized. So this is one E, and this is another E. This is fourth E. This is fourth E, and sorry, third E. This is fourth E. So energy, exergy, economic, environmental, and economic analysis. So this is what called 4E analysis for all configurations have been done. And then in this, the supplementary firing appears to be best for Indian conditions with PCFBC with supercritical power plants. But then what happens is this is about power generation. We have wider options, but ultimately we are not really. You see, these environmental issues are major problems here. Almost very large amount of economic analysis, large amount of environmental things. So if we replace the coal by solar, then convert into this one, it's called solar thermal power plants, and there are different technologies are available here. Solar power generation, we have non-mirror systems, mirror systems, and air moving systems. And in these power plant cycles for solar energy conversion, see, this CSP is the important technologies which can be used for power generation. And Rankine cycle using water and organic fluids, Brayton cycle using helium and air, hybrid cycles and Stirling cycles can be used, and a typical range of operating conditions for different thermal power cycles, low temperature, medium temperature, high temperature. These are the temperature ranges. If it is below 100, it's a low temperature, 100 to 400, medium temperature, and greater than this is high temperature. The system, how the solar power plant works is there are solar collectors. The energy from the sun is converted into heat by solar thermal collector and subsequently used to drive the heat engine. This is a cycle which can drive, and then it's connected to the electrical loads. Either it can be a grid connected or standalone. This is what we call thermal collectors, but there is a photovoltaic system also. Photovoltaic sun's energy is converted directly into electricity. In order to improve the reliability, storage is included in this and auxiliary systems. This is a typical power plant, and you, as I mentioned earlier, what we are doing is, so far we have done several, you have seen several cycles, but if those heat is replaced by solar, it's called solar CSP power plant. But see, now this is a power plant which operates on Rankine cycle. Water is a working fluid here, and in this the heat is supplied in boiler. This is a boiler, and this is a turbine. This is a condenser. This pump. The heat is supplied in this source, and this is the sink where heat is rejected, and it produces work here. But this heat is supplied by this coal. This is a coal. This is coal burning, and if we replace this coal by sun, then it's called solar, concentrating solar power. But how do we use this heat? How do we convert the sun's energy into heat? There are different technologies here. These are the 4 different technologies which convert solar energy into heat and subsequently use. This is parabolic trough, linear dish, parabolic dish, and linear funnel reflector, and power tower. These are the 4 technologies which convert solar energy into heat and which can be integrated with power plant. So therefore, this CSP technology based on the temperature, because I have mentioned here, these are 4 technologies. They have also mentioned temperature ranges. If you put this medium temperature 100 to 400, these two, the Fresnel lens and then parabolic trough, whereas power tower and then parabolic dish are used for high temperature applications. Now, if they work, what happens is if you replace this by this, it works only 8 to 10 hours. Then what you have to do? What you have to do is we have to go for energy storage. Energy storage is expensive, and then almost 8 hours means remaining 16 hours we require energy storage or auxiliary. So therefore, why we have already coal power plants, why don't we integrate solar systems to the coal? Then they call solar aided coal power plants. This is what I have mentioned in my title, because this is the 4E analysis of that. See, a typical coal-based power plant looks like this. Is a turbine generator, it produces electricity here, and this is a condenser, and heat is rejected into water body, and then it's a boiler. It goes, after that it goes here. This is a cycle. But before this boiler, the coal is burnt here. But before the water goes into the boiler, you take water from the condenser, cold water, and heat it in solar field and send it back to the boiler. This is called coal. It works. Suppose if there is no sun here, then it will work directly. It will go. This operates with coal. When the sun is there, then the solar energy comes here, because we have almost 300 clear days and then clear sky days, sunny days, and 600 to 2200 kilowatt hours per meter square is available, and which is about 2 lakh megawatt equivalent, which is the energy potential is about only 4% of the Indian desert is enough to produce this. So therefore, with this, if you go for solar, what happens is there is a fuel conservation or power boosting mode. Either it can increase the power or reduce the coal. So that if you reduce the coal, what happens is the environmental issues come down. So therefore, there are two options: bulk substitution option and individual substitution option, depending upon the deaeration. Where we inject this here is an important thing. And based on the solar aided feed water heater, we have done performance index, and with Exergy and energy performance indices here with the different feed water heatings, and then the Exergy energy power performance indices are defined here. They are in case of energy power indices, it's excess power generated over the design rated capacity by the energy input to the solar collector field. That is given here, and then Exergy excess power generated over the design by Exergy inputs given here. This is what this one. And based on our analysis, it is found that the HP feed water heater 2 is a best attractive option to replace the solar solar heat into this. So therefore, in turn, the emissions are reduced by substantially, and then increase the efficiency. Then best option is this. The annual reduction of so many tons of almost 49,000 of coal and carbon dioxide results. So it's very important to go for the solar substitution in coal-based power plant, because now coal being expensive proposition. So now we have done standalone, even CSP 4E analysis of standalone power plant has been carried out. And this is a 5 megawatt power plant and to the 50 megawatt power plant with this. Suppose if coal is there, if coal is not there, how the power plants work? We have done Exergy energy efficiencies for standalone power plants with the 50 megawatt LFR, and it's about 12.17% and 17.17% of Exergy and energy and Exergy efficiencies are reported here with respectively for different technologies. And we have developed this because this is more of analysis. We developed some concentrating photovoltaic systems, concentrating solar dish system, solar systems, which are thermal systems. These are dish. This is the PV panels and solar troughs and CSP concentrators, desalination. This is our lab at IIT-Madras. Our approach is 4D approach design. 4E you have seen. Now 4D is the 4D approach through 4E analysis. 4D means design, development, demonstration, and deployment approach of this. Then analysis is 4E: energy, exergy, and economic and environment and economic analysis. And this is we have done for solar dish collector with a different analysis with the various. This is the dish. The solar radiation concentrates into this. This is a boiler actually. This boiler is goes to the turbine. Steam goes to the turbine after expansion, after heating. And we have come up with a study entire India with a power plant and an atlas made standalone solar power dish technologies. And we have come up with a different criteria. Wherever this green area is there, that is commercially viable. Blue areas are conditionally viable, and these red areas are not viable for solar power generation. So therefore, based on the land use, land is more expensive, and then levelized cost of energy generation is also an important role. This is our prototype system for testing. This is a mini power plant on fourth roof of the fourth story building, our classroom complex. This is a parabolic trough concentrator, parabolic dish, and this is a dish, and this is another small process heat application. This is a process heat, and that is a power generation. This is power generation. And we have set up this in a school close to Chengalpat, that is Vellipuram in Kanchipuram district, and in a school, G.D. Krishnamurthy Foundation School, we installed this with energy storage here, and then this expansion tank and all. It produces 50 bar pressure at about 350 to 400 degrees Celsius, and this it gives about 50 kilowatt thermal, and now 50 kilowatt, 500 kilowatt electricity. This is another dish technologies. This is the boiler actually, boiler, which in a large scale. This is a single scale, and you can see here it is about 40 meters area, and then almost 7, 8, 3 plus 7, almost 10 to 12 meters taller, and so on. This is another dish technology. And we have come up with the standalone parabolic trough collectors across the India. Wherever red is the not viable, this green one, blue ones are viable, and I have given the statistics with the cost benefit ratio. This is a benefit to cost ratio, and levelized cost of electricity generation, and then other parameters, NPV, and other parameters are given, net present value, and so on. This is a complete comprehensive economic analysis, and because I'm not going to these values, you can see these values, and it's attractive values depending upon the capacity. So now integration, first 4E analysis for various coal power, various for fossil fuel power generation is very important, and but that will have a kind of indicators to where inefficiencies exist, and then accordingly we can correct the or improve the performance of these systems. But apart from that, in order to make these more sustainable, we have to go for solar aided power generation, and where across the India, how if the power plants are established, set up, then how we can come up with an economic operating conditions. So with this, I think I have touched upon these various aspects of this. I'll come to the conclusions of this one. Mainly, the integration is important, and then single reheat with the supercritical power plant with having a higher efficiency of 39.5%, and optimized double reheat supercritical power plants with a 40%, 43%, and then integrated gasified combined cycle is about 39.7% is obtained, and then there is the highest potential of about 44.6%, and then IGCC is also another option with imported ash, imported low ash coals gives the maximum possible plant energy efficiency of 42.2%, 45% in Indian condition. So ultimately, the solar feed water heater is very important. It conserves fuel about 5 to 6%, and 7% unit cost of electricity generation is often. Then if you go for like some of you are working in these areas, then how do we project for the future? So we have come up with a three things: short term, medium term, and long term. And with the 4E analysis, we found that this is for short term configuration, then this is the medium term, and long term is these different types of power generations. I have given all the abbreviations before. So therefore, this is a strategy to recommend for the power sector, and one of our PhD students has done this work and then come up with this, and some recommendations are given to the electricity boards and so on. So with this, I end the talk. Thank you very much. And if you have any questions, clarifications, please let me know. Thank you so much. I hope you heard everything. Hello?
Sanjay,
Can you hear me? Hello?
Yes, sir, we can hear you, sir. Just a minute.
Yes, sir, we can hear you, sir.
Okay, I hope you heard everything. Or any disconnection?
No, sir, there was no disconnection. So now,
Okay.
if the audience has any questions for sir, we can now field questions.
I hope I am on time. They can even put in the, what is that, chat box also, no problem. Where is the chat box? Chat box is there or not? Huh?
chat box இருக்கா? சொல்லுங்க. கேக்குறா பாருங்க.
So we do have the chat box available. So as far as I know, there is no questions in the chat box, sir.
Okay, perfect. If there are no questions, I thank the organizers as well as participants for giving me the opportunity. If you can, if you have questions, we can also post them and send to me by email.
Yes, sir, definitely, sir. Sir, thank you for your informative session, sir.